Yeah, let us do further with the interfacing of the microcontroller. Let us see and revise the stepper motor that we have seen in the previous lecture. Here we have seen the stepper motor inside. It is having two main parts, stator and rotor. Which is stationary, doesn't move, is the stator, and rotor which rotates is the rotor. So here are the poles around which the copper coils are wounded. We are going to energize these copper coils one by one so that the rotor can move at particular state. So as this rotor moves in particular state, it is called as a stepper motor. Then we have seen the specification of stepper motor, like rated voltage, current, step angle, number of phases, motor length, 4-wire 8-inch lead, 200 steps per revolution, 1.8 degrees, that is the step it moves, operating temperature, at which temperature it can withstand, then torque and all. So we have seen all this specification of the stepper motor. When we go to the market, we can ask shopkeeper with this specification to give the stepper motor. So here is the stepper motor, this is the shaft of the motor, here are the wires or coils that we can use. There are the 4 coils, blue, red, yellow, green. Black and white are the common terminal taken out of those coils. Next, we have seen how to test the wires. There is the resistance between the black and grey or black and yellow, or we can say a common and the coil. There is a X resistance and there is no resistance out of between the two coils, or it is 2X. These are the coils A, B, C, D, and we have taken common out of that and given to the power supply. This is the stepper motor, how it looks when we get it ready-made into the market. For interfacing, we have seen the concept that we are going to interface at one of the port. In this case, let us say it is the port 1. Stepper motor requires the current between 0.1 to 1 ampere to move it with load, and 805 microcontroller provides 0.045 ampere, that is 45 milliampere current throughout its ports. So there is the issue of compatibility. It is not possible to connect stepper motor directly to the port pins of the microcontroller. So we need one driver IC, let's say UNL 2003 we are going to use here, which is the high voltage high current Darlington transistor array. It has 7 set of this transistor array. It is made of PNP and NPN transistors connected together, where emitter of the PNP transistor is connected to the base of NPN transistor to create a sensitive transistor with high current gain. ULN 2003 takes low power input and provides the high power output. Here are the details of UNL 2003. We have seen it is having 7 set of the transistors in Darlington pair. So this side 1, 2, 3, 4 up to 7, it is to the microcontroller side. This is the base of NPN transistor, and this 16 to 10 is the collector of PNP transistor, and this 8 and 9 are ground and common, or we can say it is connected to VCC. Here we are going to energize each of the coil of the stepper motor so that it can move into the steps. Then we have understood some parameters of the stepper motor, some terminology that we are going to use, like step angle. The step angle is the angle in which the rotor moves when one pulse is applied as an input of the stator. This parameter is used to determine the positioning of the stepper motor. Next, we have seen the steps per revolution. This is important formula to compute the step angle. Next, steps per second. It is used to measure the number of steps covered in a second. Then RPM, it gives the speed, revolution per minute. It measures the frequency of rotation. By this parameter we can measure the number of rotation in 1 minute. This formula gives the relation between the RPM, steps per revolution, and the steps per second as like this: RPM into steps per revolution divided by 60, that is per second. That's why we are dividing it by 60. Next, we have seen the mode of the stepper motor, that it can move. First mode is the wave drive mode. This mode depends on the stepping sequence or energizing the windings of the stepper motor. So here we are energizing one windings at a time, so that the stepping sequence is like this: 1 0 0 0 1 0. So it is shifting. We have seen with the particular graph in previous slides how it steps out. Second mode is the full drive mode. In this mode we are energizing two coils at a time. This two, this two, this two, this two, likewise. And in this way the rotor moves in this way, and the stepper motor moves. Third mode is the half drive mode that we have seen. In this mode, what is it? At first one coil is energized, this one coil is energized, then two coils are energized. First one coil is energized and then two coils are energized. This is basically a combination of wave and full drive mode. It increases the angular rotation of the motor. So in this way we are going to energize the coil. You can see over here 2, 3, 4, 5, 6, 7, 8. You can see how the coils are energized. First one, see it again, 2, 1, 2, 1, 2, 1, 2, 1. In this way the coils are energized and stepping sequence is given to the stepper motor. Here we have seen the interfacing diagram of stepper motor with microcontroller through a ULN 2003 IC, that is nothing but the current booster IC, or we can say it is a driver IC. So 1, 2, 3, 4 are the base side connected to the any of the port of the microcontroller. We have chosen port 1 pins P1.0 to P1.3, which are connected to this 4 pins of the ULN 2003. And to the collector side we have connected the coils of the stepper motor. Let us program the stepper motor in each of the mode that we have seen. First we have seen the wave drive mode. This sequence we are going to provide for the stepper motor. Here we have declared the hardware. Port pins are given with the variable A1, A2, A3, A4. We have understood the concept of this EQU, or declaration of the variable to the hardware. EQU is the directive, these are not the instruction. So in this way we are going to describe the hardware. Starting with T-mode resistor, timer 0 in mode 1 is selected. This we are going to use for generating a delay for the stepping. So in this way we are making the particular windings high one by one. CLR A1, A coil delay, set B A1. So we are energizing this coil one by one, A1, A2, A3, A4, and in between we are calling the delay to settle down. Here is the delay routine. So here we have initialized TH0 with the 00. Lowest count gives the highest delay. That is the concept we have seen at the timer programming. So TL0, TH0 is loaded with the 0 count, so it will give the maximum count of FFFF. start the timer, wait for the flag to be raised. When flag goes, when there the end of timing action or roll or condition, stop the timer, clear the flag and do it again. So 6 R6 register, the 1D is the count loaded, so that much time this loop will be executed and that much delay will be generated out of this. So this is the way of programming stepper motor in the wave drive mode. Next is the full drive mode. Observe the stepping sequence. 2 coils are energized at a time and is the hex equivalent of this particular code. So 0C for energizing coil AB, for BC it is 6, for CD it is 3 and for AD it is 09. So you can see it is just rotation of the right. If we rotate this bit 1 right, we get this sequence. If we rotate this sequence 1 bit right, we get this sequence. Likewise. So understanding this logic, we are writing a program. Here I have chosen the bit pattern 6 and I have made as 66, so it won't affect when I do the rotation. So move A #66. Hope you understand why this magic figure 66. You can take any of the stepping sequence out of this 4. I have chosen this. So with RRC we will be getting the next bit pattern. That's why first choose any initial sequence to start with and do RRC. You will be getting the next sequence, and in this way the next coil will be energizing and the rotor will move in the step. Here is the delay routine. Same program we can write in this way. Here directly the hex code is sent to the port, so which will give the stepping sequence to the stepper motor connected to particular port pins. So P2 0C equal delay, P2 06 equal delay, P2 03 equal delay, P2 09 equal delay, and do it again. So this is the simple way of writing a program for interfacing of the stepper motor. Next is the half drive mode. In half drive mode we are having the 8 stepping sequence. So simple way, pick up the stepping sequence, send it to the port and a delay. This is the simplest way to write a program. There are many ways to write a program, but as a beginner this is the simplest way to write a program. So take the code, send to port, take the code, send to port, take the code, send to port. In this way do the programming. So this is all about we have seen for the stepper motor. Next we have to start with the interfacing of the relay and buzzer. Let us see the interfacing of relay and buzzer. Here I am. Remember the course objective. We are at principles of interfacing and programming. Today we are going to see relay and buzzer in this lecture. So let us see some introductory about the relay. What is a relay? A relay is an electromechanical switch which is used to turn on or off any circuit by using electromagnet. It is just like practical switch which is driven electronically. Due to electrical isolation properties and high load carrying capacity of the relays, they are used to control high power external devices like fans, lights and motors, etc. Relays electromagnet requires heavy current to operate, which cannot be fulfilled by the 8051 microcontroller. This concept we have seen when we have interfaced the stepper motor, because current sourced by microcontroller is just 45 milliampere, and this relay motor, the current sinking capacity of those devices are very high, that is in the range of ampere, which cannot be fulfilled by the microcontroller. So we are going to use a driver IC in between, which will make it compatible. A transistor can be used to operate the electromagnet or driver IC UNL 2003A that we have seen previously with the stepper motor. Here are two types of relays: electromechanical relays and solid state relays. Solid state relays are used for very high power devices or motor, three-phase motors like that. Today we are going to interface the electromechanical relays. So it comes into two ways, normally open and normally closed. We will be using the normally open relays. Here is the difference between the solid state relays and electromechanical relays. Due to use of zero crossing detector, solid state relays minimize the electrical noise, whereas electromechanical relays use coils which acts as inductors and they can cause electrical noise like back EMF. Solid state relays have longer life cycles as they have lesser moving parts. Due to a lot of moving parts, they have shorter life cycles in case of the electromechanical relays. Coming to the solid state relays, they are faster. They have faster response time and lower power consumption. Opposite is electromechanical. They have slower response time as the mechanical switches control the external devices. Solid state relays are used for high power devices and it used for the heavy load. So optocouplers are used to controlling mechanism. Use of electromagnets for the controlling mechanism in case of the electromechanical relays. As highly resistant to shocks and vibration as they do not have a lot moving parts. In case of electromechanical relays, they are not resistant to vibration as they have a lot of moving parts. Solid state relays can be used in places with the high electromagnetic forces, whereas electromechanical relays cannot be used in places with the high values of electromagnetic forces. So, solid state relays are costlier initially, but as they are robust, we can say they are the cost effective. But electromechanical relays are cheaper compared to solid state relays. As they use semiconductor to control output circuit, a spike in voltage can cause damage to solid state relays, whereas external variation from output side do not damage the devices as they use the physical switches. So this is the basic concept of the solid state relay and electromechanical relays and the difference between them. So for smaller load, electromechanical relays can be used. So we are going to say electromechanical relays. Here is the interfacing diagram of the electromechanical relay. We require only one pin to drive the electromechanical relay. So as we have seen the incompatibility issue, we are going to use transistor which boost the currents, which meet the current requirement of the relay. So we are going to use this transistor 2N3904 in between the relay and the microcontroller side. So here is the interfacing diagram. We are going to use normally open relay. We have to simply make the pin connected to base of the transistor high and low to on and off the relay. So here is the program. CLR P2.0, initially make it off as it is a normally off. ACOL delay CPL 2.0. So if it is off, it will be on in next slide. When it is, if it is on, it will be off. So in this way we can make it on and off. Here is the second way to write a program. Just off it, call the delay, make it on. You can do it continuously. So these are the two ways to write a program for relay. Second, program is same but the interfacing diagram is changed. Instead of transistor, now ULN 2003 AIC is used to fulfill the current requirement. That is the basic concept only. Rest of the programming is same for the interfacing of the relay. So next we are going to see is buzzer, one of the application. So buzzer are used to just make a beep, make a sound. It is just like a indicating device. If we want to indicate something, we use the buzzer. Here are the different buzzers available in the market. We can use as per our requirement. Here is the interfacing diagram of the buzzer. Same as the relay, we require the transistor to connect in between so that we can fulfill the current requirement of the buzzer and the current provided by the microcontroller. So this is the way to interface the buzzer with the microcontroller. Coming to the programming, it is same as a relay. CLR P2.0, ACOL delay, CPL P2.0. So in this way you can make the buzzer on and off. If you want a longer time on, you can call the delay multiple times so that on time of the buzzer can be increased. Here is an example. Here CLR P2.0 buzzer is off, then give some time, set B P2.0, make it on. You can call a delay twice, thrice so that your on time of buzzer you can increase. So as per requirement it is done. So this is the another way to interface the buzzer through IC, and here is the program. That is all about the buzzer. So it is so simple to interface the buzzer and relay. The interfacing concept is same, writing a program is same. Here are the possible questions that can be asked. Interface relay with 8051 microcontroller. Write a program to make a relay on or off continuously. Draw the interfacing diagram and explain it. For buzzer, it is asked in the same way. Interface it, write a program, but here timing is mentioned. Buzzer should on for 2 seconds. So in this case, delay can be generated using the timer so that you can fulfill the requirement of 2 seconds. So that is all about the interfacing of buzzer and relays.